Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.
Welcome to the Computer Chronicles. I'm Stuart Chaffee, and sitting in for Gary Kildall this week is Herb Lechner. On today's program, we're going to be delving into the mysterious computer chip itself, that tiny piece of silicon that seems to be able to hold so many circuits. Herb, we have moved along from 8-bit to 16-bit, even 32-bit processors, from 16K chips. We even hear talk now of 256K, 4 megabit memory chips. How far can we go in jamming stuff into these computer chips?
Well, I'm embarrassed to admit, Stuart, that about 10 years ago when I was asked that question, I responded that I thought we were approaching the limit because I assumed that the components of computing would continue to be a few inches or a foot apart, and light only travels a foot in 1 nanosecond. But obviously micron distances have proved me wrong today.
So who knows how far we can go.
Who knows how far we can go.
Before we get into chip architecture itself, let's take a look at silicon, the natural material which is the basis for all this semiconductor technology.
Integrated circuits, computers on a chip, micro-miniaturization. The semiconductor that makes these revolutionary devices possible is derived from one of the most common materials in the Earth's crust, silicate. The purified extract, silicon, is heated until it becomes molten, and a seed crystal is dipped into the melt and slowly drawn out. As the seed crystal is withdrawn, the molten silicon crystallizes, forming a single crystal or ingot. The ingot is sliced into thin wafers. Once polished and microscopically cleaned, these brilliant discs are the foundation for integrated circuits. The process of transformation begins with computer-aided design, a method that calls up circuit design modules from the computer's memory. A new design can be created and edited with the stroke of a light pen and a video screen. But the printout of computer-edited copy is routinely checked against the hand-drawn design, still, at present, the final document. If they match, the data is converted to a photographic mask, and through photolithography, the design is transposed onto the wafer. A chemical wash develops the pattern by dissolving away, or etching, sections exposed through the mask. As each layer of circuitry is applied, it is checked for alignment with the others. This step becomes critical as large-scale integration is replaced with very large and soon super large-scale integration, a jump from 10,000 to 100,000 transistors on a single chip.
Our guest on today's Computer Chronicles is Phil Downing. He's Vice President for Corporate Technology at Advanced Micro Devices, sometimes known as AMD. Herb?
Phil, there's been so much development and we've come such a long ways from vacuum tubes to today's integrated circuits. Can you start out by giving us just sort of a quick view of where are we today?
Well, as you know, Herb, today we're able to put thousands of transistors onto a single chip and virtually take an entire computer and put it on. And we do this with photolithography type of processing that enables us to pattern images down at the 1 micron size. This not only allows us to build microcomputer chips, but also memories having densities of thousands of bits, 64,000 bits, 256,000 bit memories.
Well, have we exhausted the technology? Have we come as far as we can, or is there more to go?
No, we see the trends over the last decade in which the feature sizes that we use to make these chips going down at about 10% per year, continuing over the next decade. We'll still be able to reduce the feature sizes below 1 micron.
What technology does it take to allow you to make things that small? How are you able to make them down to the size of a micron?
It used to be simple contact printing. The photographic images were put onto a plate which is brought into contact with the material being processed, and simple contact printing image transfer. What's happened in the last 10 years is that we've moved to a projection imaging capability that allows us to not only get very, very fine feature sizes, but because we don't bring the mask into contact with the wafer, we don't damage the material during processing. That gives us very few defects in the manufacturing process And with very few defects, we can now make these very complex circuits economically.
Do you run into quality control problems as you get greater and greater scales of integration? I mean, do you end up with fewer acceptable chips?
Well, as the feature sizes go down, the number of defects that you can capture during the process increase. And so we have to maintain more and more clean conditions in our manufacturing process. This does translate into more difficulty in the process, but we evolve our quality control measures as we develop the technology so that we can do it economically. Also, there are means of building extra circuitry into some of these chips so that you can program out during testing faulty portions of the chip and end up with reconstructed good chips. This is called redundancy. And this also helps maintaining the quality and also the economics of building these chips.
How hard is it to design a chip? I know that you run tens of millions of chips once they are designed, but I also know that there are a number of chips on the market. How do you go about designing a chip or modifying one?
The design is probably one of the most complex tasks that faces today. We talk about the evolution of the microelectronics technology, but many people in our industry have stated that the technology is moving faster than our ability to design these complex chips. And so what we've had to do is to change the way we design the chips. It used to be that with a collection of 100 or several hundred components on the chip, you could define a small system, a set of AND gates, OR gates, a multiplexer, or something like that, and you could draw this up on a piece of paper, on a precision graph, and then this could be translated into a set of photographic plates for processing. These days, when you're talking about having 100,000 transistors on a chip, the task can no longer be handled by drawing individual components on a piece of paper. So we have to use computers to maintain these huge files of various geometries that ultimately get translated into the chip process, and that's called computer-aided design. And that's an area that requires a great deal of development in the next decade for us to capitalize on what the technology is going to be capable of doing.
What are the trade-offs as you go to faster and faster movement of electrons through the chip in terms of heat generation? Do you reach a point where you start to create a problem?
Absolutely, and in fact, one of the latest technologies that people talk about today, complementary MOS technology, many people call it CMOS technology, addresses that very problem. And that is that each element or each logical element on the chip consumes a certain amount of power, and different circuit and device technologies consume different amounts of power for each element. In bipolar technologies is a large amount of power consumed for each element to gain very high performance. In NMOS technologies, there is still a moderate amount of power consumed, and for levels of complexities that we deal with today, the power consumption is handleable. But as we build the complexity to hundreds of thousands of components on a chip, the power consumption by each element is unacceptable, even in NMOS technology. And so you have to use a technology like complementary MOS, which doesn't burn any power during its static operation. Only when it switches does it consume power. And this is very key for us in building more complex chips.
Can these technologies be both used in the same computer?
Oh, absolutely. In fact, many companies like ourselves offer multiple technologies in the products that they deliver. And we put together kits of products that are made to work together that use bipolar technology, NMOS technology, and as CMOS technology comes into its own in this decade, all three of those technologies will be used together.
Phil, you mentioned that the chip technology maybe is ahead of your ability to design for that technology. I've also heard that your chip technology is kind of ahead of our ability to actually apply it and use the amount of integration you can get on a chip. Is that true?
Well, now you're getting into the systems area, and that's not my area of expertise, but being a user of computers and computer-aided design, we certainly see an broad application of hardware to solve the software problem. We substitute a great deal of computational capability for clever software design. And we find that higher and higher levels of integration and software capability are crucial to us in our design task. Engineering workstations that give the power of 1 million instruction per second computer at the hands of each individual engineer is something that we very definitely can use.
We've heard about the possibility of 4 megabyte chips. I mean, is that a conceivable project?
Well, I think people would feel very happy if we could conceive of a 4 megabit chip.
Megabit, okay.
If you look at today's state of the art, IBM has recently announced a prototype version of a 512-bit dynamic memory. And there is a project that's being proposed for the Semiconductor Research Corporation to actually develop a 4 megabit dynamic memory. And we certainly think that it's feasible to accomplish that in the next 4 or 5 years.
Let me ask you about the material itself. We're talking about silicon primarily
That's right.
in chips. Is that the material of the future forever for chips, or is there another element that might solve some of your problems?
It's a very application-sensitive topic, and that is for microwave types of circuits and for light-emitting diodes or optical-type chips where you're looking for optical interfaces. Other materials in silicon are suitable for that. Indium phosphide, gallium arsenide probably being the most popular of them. However, if you're talking about VLSI, very large-scale integrated circuits, we really see silicon as being the material that's going to dominate in the foreseeable future.
Okay, in just a minute we're going to take you on a guided tour of a computer chip. That's coming up next. Okay, Phil, you're holding 2 chips, I guess, in that case. Tell me what it is you have there.
Well, I have a chip that was designed in 1975. This is the 2901 chip, which is a 4-bit slice microprocessor. And next to it, you see a much larger chip, which is a 16-bit microprocessor, which is called the AM29116. This chip, being a 16-bit microprocessor, is roughly 5 times the component complexity of this one here. And I have a photomicrograph of this smaller chip. This is about 1/8 of an inch on a side here, and so you can see that this is quite a large blow-up.
Okay, now this, in fact, is the 4th generation of this particular chip, isn't it?
That's right. The 2901C, we go 2901, and then the 2901A was introduced, B and C, so this makes it the 4th one.
Okay, and what kind of chip is this?
This is a 4-bit bit slice microprocessor.
Okay, and could you take us through a tour of all the components that are crowded inside that tiny thing?
Well, 4-bit slice microprocessor is basically an ALU with a register file and a set of instruction decoders and, of course, an input-output section. Now, what you see in the center here is the register file. This is a 2-port RAM so that it can both read and write different bits of the memory at the same time. It takes the data, the 4 bits of data out of this register file and pumps it through this section here, which is the ALU, which is controlled by the instruction decode, which you see up in this section here and some of it in this section over here. So the random logic that you see that's very irregular is what makes up the instruction decoding. ALU is quite a regular structure, as is the register file here. You can see the outputs along the section here and a set of inputs along the side of the chip here for control and data input.
Okay, and ALU for people who don't understand.
Arithmetic logic unit.
Okay.
This is the part that does the work.
Right. Now, explain to me, you said it's been improved now 3 different times to get to a 4th generation. What does it mean to improve this chip each time you redesign it?
There have actually been 3 things done with this chip to improve it. One of them is simply capitalizing on changes in our photolithographic processing. The lines get narrower because the manufacturing capability improves, and we want to capitalize on that to make it smaller. Making it smaller does 2 things all by itself. It makes it more economical to build, and it also improves the performance of the chip because as the individual devices get smaller, their performance improves. 2 other things have been done. One, we have changed the bipolar technology with which the chip is made to improve its performance characteristics. That has had an obvious benefit. And also we've changed the circuit technology. This chip was originally designed in a TTL circuit technology, and we changed to what is called an ECL, or emitter coupled logic technology. It's a different bipolar circuit design approach, and this has in fact changed the operational speed of the circuit by about a factor of 2. All in all, we have accumulated about a 4x improvement in performance by redesigning the chip 4 times.
Phil, it's been said by some that the Japanese are pulling ahead of us in the design and manufacture of advanced microchips. Do you agree with this? And if so, what is our response to that?
The Japanese have certainly come a long way in the last decade. 10 years ago, they were not a significant factor in the integrated circuit business, and today we could consider them a very worthy competitor, especially in the memory area. The Japanese, I think it's well known that they have excellent manufacturing capability, and they also have excellent capital formation, which gives them a significant competitive edge over our industry in the United States. The response, at least from advanced micro devices, and I believe it's characteristic of the industry, is to be very innovative in the products that we build, so that we expect that the new products that we introduce will allow us to maintain profitability in our industry.
What about the fifth generation project we hear about in Japan? How dependent is a fifth generation computer on increased levels of integration?
Well, again, you're getting outside my area of expertise, but certainly the chip technology is considered to be very key because of the enormous computational requirements of that type of a system. It's, I think, pretty widely held that you need very sophisticated distributed processing in order to implement this kind of a system, the fifth generation computer, and inexpensive arrays of microprocessors is going to be key in making that happen.
I believe the Japanese have talked about having as many as 100,000 switches on a given chip. Is that a proper recollection?
Well, that's true. That's, in fact, below the state of the art of the industry today.
Oh, it is?
Yes. Western Electric and IBM and even ourselves have built chips with several 100,000 components on a chip. If you look at this other chip here, we have a 256K EEPROM here, which has one transistor for each bit of memory, obviously. And so that means that it has more than 250,000 components on one chip. And there are microprocessors that have been built in the industry today that have 500,000 components on a chip.
Is standards a problem in your end of this business? It seems to be a problem in every aspect of this computer business. AMD, you have your chips, and Intel has its, and Zilog, and so on. Does that complicate this field in any way, or in terms of looking at, say, networking and Ethernet type standards and so on? Is standards an issue in your industry?
Most definitely. We participate strongly in the definition of network standards, especially at the lower levels of network protocol. The physical layer and the link layer in the protocol structure is something that if we don't have a good standard definition, it's very hard for us to get a good part defined. And since we invest years of design activity in many of these complex parts, we can't afford to be wrong. So standards are a very important element of our business.
How do you handle the standards problem as we get more and more into the manufacture of specialized or custom chips?
Actually, in two ways. One is that we have to be very capable in terms of defining complex products, obviously, and although there are many who would believe that it's not possible to continue to do that with increasing levels of complexity, that statement's been made for the last 20 years. And we do believe that there is a large market for standard components, large, high-volume type of parts,
and
similar to this, and that will continue.
Mm-hmm.
However, we also see that there will be a growing market for semi-custom and custom-type parts. And that'll come about mainly because the design problem that we face today in building standard components forces us to automate the design process just for our own purposes. It costs us millions of dollars today to design a microprocessor. We have to solve that problem for ourselves, and in solving it for ourselves, we'll develop tools that enable us to design semi-custom and custom chips efficiently. Mm-hmm. And in fact, today, many systems manufacturers do design their own chips with some of the sophisticated tools that are available today IBM builds many of their systems with gate array components, which are semi-custom integrated circuit products. So we will see an increasing share of the market taken by custom and semi-custom type chips.
Phil, we have just about a minute left. Let's look 5 years down the line. What are we looking at as the next major advance or next major improvement in chip technology?
Well, as I said, the technology that you will see emerging in the next few years as a dominant technology is CMOS, because of the fact that it can build chips of very high complexity without a power consumption problem. And then beyond that, I think that you're going to see a continuation and evolution of the memory technology that will take us to the 4 megabit memory level and beyond that. So I think that we will see technology continue to decrease the cost per function. Today we're looking at somewhere homing in on 1 millicent per bit memory prices. And we're going to see a half a millicent and a quarter of a millicent per bit in the future.
Okay, we're all out of time. Phil Downing of AMD, thanks very much for joining us, and we'll see you again next week on Computer Chronicles.
Microfocus, creators of visual programming tools for software development, is pleased to provide major funding for the Computer Chronicles, the story of this continuing evolution.